This is homework 2, part A1. So for this one, we need to derive an expression for the vertical force on the spherical end cap of a horizontal capsule with cross-sectional radius r that is half filled with fluid. So this one's pretty simple. So first I drew the cylinder. So we have our Fx and our Fy, which is what we're going to be focusing on, and then our radius r. So we know that for a similar problem with the cylinder, to find the force, all we need to do is take the cross-sectional area. So we could do that for the whole cylinder, but this question is asked us for one of the caps. So we know that the area of a sphere is 4/3 times pi times radius cubed. That's just the volume of a sphere. And we know that since the water is only at half, that cuts the sphere in half. And then since we're only focusing on one side of those half spheres, that we're only focusing on 1/4 of that volume. And the force is just a rho times gravitational constant times area. So we have the area radius, so we multiply it by, or pressure times gravitational constant, and that is our Fy. This is homework 2, part A, part 1. So for this one, we need to derive an expression for the vertical force on the spherical end cap of a horizontal capsule with cross-sectional radius r that is half filled with fluid. So first, we're going to look at like a diagram for this one. I've already drawn that. So we have two forces here. We have F of x and Fy. And then we also have our radius of the sphere, r. So for this one, we're only going to be worried about F of x. That is actually the downforce. So for F, we're just going to do vertical. F vert, that works. And then we're going to be, that's equal to the volume of the sphere, which is 4/3 pi r cubed. And since we only have 1/4 of the radius, we're going to multiply that by 1/4. And also times rho g. Okay, so now we need to integrate to find f of x. So f x equals the integral of d f x. That is equal to pressure times d a. I'll keep going. So the integral of that, so pressure times g times the h. And so I'm going to go back up here. So we have our height here and our radius here. And so we need the x component of this, so it would be this value, which would be the square root of r squared minus h squared. So we're going to add that to this. R squared minus h squared. We're integrating with respect to dh. And then the limits are going to be from 0 to r, because that's the radius. This is a 2. Okay, so now we're ready to start integrating a little bit more, but we have to do integration by parts. So our u is going to be r squared minus h squared du is equal to -2 h d h. So now we can take these out. So we get negative p g, and these don't get integrated because they're constants. That's gonna be 0 since we made these negative. So now r squared on the bottom, 0, and it'll just be u to the 1/2 because it's square root times d u. All right, so now we can actually evaluate. So we're gonna do 2 over 3 dg, and then you get 2/3 from evaluating this integral here. Then u to the 3 over 2. And because we had this negative here, we're going to flip this, and now r squared will be on the top. 0. Okay, so when we evaluate that, we get 2 over 3 p g, and then r cubed when you plug that in here, and then -0, obviously. So that's pretty much our answer. So we're going to write down one more time. F x equals 2 over 3 p g times r cubed. Okay.